Born in 1773, Young was the eldest of 10 children. He was reading fluently by the age of 2 and had read the entire Bible twice by 6. A master of more than a dozen languages, Young went on to make important contributions towards the deciphering of Egyptian hieroglyphics. A trained physician, he could indulge his myriad intellectual pursuits after a bequest from an uncle left him financially secure. His interest in the nature of light led Young to examine the similarities and differences between light and sound, and ultimately to one or two difficulties in the Newtonian system. Convinced that light was a wave, he devised an experiment that was to prove the beginning of the end for Newton's particle theory. Young shone monochromatic light onto a screen with a single slit. From the slit, a beam of light spread out to strike a second screen with two very narrow and parallel slits close together. Like a car's headlights, these two slits acted as new sources of light, or as Young wrote, as centers of divergence, from whence the light diffracted in every direction. What Young found on another screen placed some distance behind the two slits was a central bright band surrounded on each side by a pattern of alternating dark and bright bands. To explain the appearance of these dark and bright fringes, Young used an analogy. Two stones are dropped simultaneously and close together into a still lake. Each stone produces waves that spread out across the lake. As they do so, the ripples originating from one stone encounter those from the other. At each point where two wave troughs or two wave crests meet, they coalesce to produce a new single trough or crest. This was constructive interference. But where a trough meets a crest or vice versa, they cancel each other out, leaving the water undisturbed at that point. Destructive interference. In Young's experiment, light waves originating from the two slits similarly interfere with each other before striking the screen. The bright fringes indicate constructive interference, while the dark fringes are a product of destructive interference. Young recognized that only if light is a wave phenomenon could these results be explained. Newton's particles would simply produce two bright images of the slits with nothing but darkness in between. An interference pattern of bright and dark fringes was simply impossible. When he first put forward the idea of interference and reported his early results in 1801, Young was viciously attacked in print for challenging Newton. He tried to defend himself by writing a pamphlet in which he let everyone know his feelings about Newton. But as much as I venerate the name of Newton, I am not therefore obliged to believe that he was infallible. I see not with exultation but with regret that he was liable to error, and that his authority has perhaps sometimes even retarded the progress of science. Only a single copy was sold. It was a French civil engineer who followed Young in stepping out of Newton's shadow. Augustin Fresnel, 15 years his junior, independently rediscovered interference and much else of what Young, unbeknownst to him, had already done. However, compared to the Englishman, Fresnel's elegantly designed experiments were more extensive, with the presentation of results and accompanying mathematical analysis so impeccably thorough that the wave theory started to gain distinguished converts by the 1820s. Fresnel convinced them that the wave theory could better explain an array of optical phenomena than Newton's particle theory. He also answered the long-standing objection to the wave theory. Light cannot travel around corners. It does, he said. However, since light waves are millions of times smaller than sound waves, the bending of a beam of light from a straight path is very, very small and therefore extremely difficult to detect. A wave bends only around an obstacle not much longer than itself. Sound waves are really long and can easily move around most barriers they encounter. One way to get opponents and skeptics to finally decide between the two rival theories was to find observations for which they predicted different results. Experiments conducted in France in 1850 revealed that the speed of light was slower in a dense medium such as glass or water than in the air. This was exactly what the wave of light predicted, but while Newton's corpuscles failed to travel as fast as expected. But the question remained, if light was a wave, what were its properties? Enter James Clerk Maxwell and his theory of electromagnetism. Born in 1831 in Edinburgh, Born in 1831 in Edinburgh, Maxwell, the son of a Scottish landowner, was destined to become the greatest theoretical physicist of the 19th century. At the age of 15, he wrote his first published paper on a geometrical method for tracing ovals. In 1855, he won Cambridge University's Adams Prize for showing that Saturn's rings could not be solid but had to be made of small, broken bits of matter. In 1860, he instigated the final phase of the development of the kinetic theory of gases. The properties of the gases explained by maintaining that they consisted of particles in motion. But his greatest achievement was the theory of electromagnetism. In 1819, the Danish physicist Hans Christian Ørsted discovered that an electric current flowing through a wire deflected a compass needle. A year later, the Frenchman François Arago found that a wire carrying an electric current acted as a magnet and could attract iron filings. Soon his compatriot André-Marie Ampère demonstrated that two parallel wires were attracted towards one another if each had a current flowing through it in the same direction. However, they repelled each other if the currents flowed in the opposite directions. Intrigued by the fact that a flow of electricity could create magnetism, the great British experimentalist Michael Faraday decided to see if he could generate electricity using a magnetism. He pushed a bar magnet in and out of a helix coil wire and found an electric current being generated. The current ceased whenever the magnet was motionless within the coil. Just as ice, water, and steam are different manifestations of H2O, Maxwell showed in 1864 that electricity and magnetism were likewise different manifestations of the same underlying phenomenon, electromagnetism. He managed to encapsulate the disparate behavior of electricity and magnetism into a set of 4 elegant mathematical equations. On seeing them, Ludwig Boltzmann immediately recognized the magnitude of Maxwell's achievement and could only quote Goethe in admiration. Was it a god that wrote these signs? Using these equations, Maxwell was able to make the startling prediction that electromagnetic waves traveled at the speed of light through the ether. But if he was right, then light was a form of electromagnetic radiation. But did electromagnetic waves actually exist? If so, did they really travel at the speed of light? Maxwell did not live long enough to see his prediction confirmed by experiment. Aged just 48, he died from cancer in November 1879, the year Einstein was born. Less than a decade later, in 1887, Heinrich Hertz provided the experimental corroboration that ensured Maxwell's unification of electricity, magnetism, and light was the crowning achievement of 19th century physics. Hertz proclaimed in his paper outlining his investigations, "The experiments described appear to me, at any rate, eminently adapted to remove any doubt as to the identity of light, radiant heat, and electromagnetic wave motion. I believe that from now on we shall have greater confidence in making use of the advantages which this identity enables us to derive both in the study of optics and electricity." Ironically, it was during these very experiments that Hertz discovered the photoelectric effect that provided Einstein with the evidence for a case of mistaken identity. His light quanta challenged the wave theory of light that Hertz and everyone else thought was well and truly established. Light as a form of electromagnetic radiation had proved so successful that for physicists to even contemplate discarding it in favor of Einstein's light quanta was unthinkable. Many found light quanta absurd. After all, the energy of a particular quantum of light was determined by the frequency of that light, but surely frequency was something associated with waves, not particle-like bits of energy traveling through space. Einstein readily accepted that the wave theory of light had proved itself superbly in explaining diffraction, interference, reflection, and refraction, and that it would probably never be replaced with another theory. However, this success, he pointed out, rested on the vital fact that all these optical phenomena involved the behavior of light over a period of time, and any particle-like properties would not be manifest. This situation was starkly different when it came to the virtually instantaneous emission and absorption of light. This was the reason Einstein suggested why the wave theory faced especially great difficulties explaining the photoelectric effect. A future Nobel laureate, but in 1906 a Privatdozent at Berlin University, Max Lau, wrote to Einstein that he was willing to accept that quanta may be involved during the emission and absorption of light. However, that was all. Light itself was not made up of quanta, warned Lau, but it was when it was exchanging energy with matter that it behaves as if it was consisted of them. It consisted of them. Few even conceded that much. Part of the problem lay with Einstein himself. In his original paper, he did say that light behaves as though it consisted of quanta. This was hardly a categorical endorsement of the quantum of light. This was because Einstein wanted something more than just a heuristic point of view. He craved a fully fledged theory. The photoelectric effect had proved to be a battlefield for the clash between the supposed continuity of light waves and the discontinuity of matter, atoms. But in 1905, there were still those who doubted the reality of atoms. On the 11th of May, less than 2 months after he finished his quantum paper, the Annalen der Physik received Einstein's second paper of the year. It was his explanation of Brownian motion, and it became a key piece of evidence in support of the existence of atoms. When in 1827 the Scottish botanist Robert Brown peered through a microscope at some pollen grains suspended in water, he saw that they were in a constant state of haphazard motion, as if buffeted by some unseen force. It had already been noted by others that this erratic wiggling increased as the temperature of the water rose, and it was assumed that some sort of biological explanation lay behind the phenomenon. However, Brown discovered that when he used pollen grains that were up to 20 years old, they moved in exactly the same way. Intrigued, he produced fine powders of all manners of inorganic substances, from glass to a piece of the Sphinx, and suspended each of them in water. He found the same zigzagging motion in each case. And realized that it could not be animated by some vital force. Brown published his research in a pamphlet entitled A Brief Account of Microscopical Observations Made in the Months of June, July, and August 1827 on the particles contained in the pollen of plants and on the general existence of active molecules in organic and inorganic bodies. Others offered plausible explanations of Brownian motion, but all were sooner or later found wanting. By the end of the 19th century, those who believed in the existence of atoms and molecules accepted that Brownian motion was the result of collisions with water molecules. What Einstein recognized was that Brownian motion of the pollen grain was not caused by a single collision with a water molecule, but was the product of a large number of such collisions. At each moment, the collective effect of these collisions was the random zigzagging of the pollen grain or suspended particle. Einstein suspected that the key to understanding this unpredictable motion lay in deviations, statistical fluctuations from the expected average behavior of water molecules. Given their relative sizes, on average, many water molecules would strike an individual pollen grain simultaneously from different directions. Even on this scale, each collision would result in an infinitesimal push in one direction, but the overall effect of them would leave the pollen unmoved as if they cancelled each other out. Einstein realized that Brownian motion was due to water molecules regularly deviating from their normal behavior, as some of them got bunched up and struck the pollen together, sending it in a particular direction. Using this insight, Einstein succeeded in calculating the average horizontal distance a particle would move as it zigzagged along in a given time. He predicted that in water at 70 degrees Celsius, suspended particles with a diameter of 1,000th of a millimeter would move on average just 6,000ths of a millimeter in 1 minute. Einstein had come up with a formula that offered the possibility of working out the size of atoms armed only with a thermometer, microscope, and stopwatch. 3 years later, in 1908, Einstein's predictions were confirmed in a delicate series of experiments conducted at the Sorbonne by Jean Perrin, for which he received the Nobel Prize in 1926. And finally, there's a break. Okay, we got 6 pages left. We got this, y'all. We got this. Actually, there's 5 pages left. Why am I saying 6? We got this. I got this. We got this. Alright, let's go. With Planck championing the theory of relativity and the analysis of Brownian motion recognized as a decisive breakthrough in favor of the atom, Einstein's reputation grew despite the rejection of his quantum theory of light. He received letters often addressed to him at Bern University, as few knew he was a patent clerk. I must tell you quite frankly that I was surprised to read that you must sit in an office for 8 hours a day, wrote Jakob Laub from Würzburg. History is full of bad jokes. It was March 1908 and Einstein agreed. After almost 6 years, he no longer wanted to be a patent slave. He applied for a job as a mathematics teacher at a school in Zurich, stating he would be ready and willing to teach physics as well. With his application, he enclosed a copy of his thesis that had earned him, at the third attempt, a doctorate from Zurich University in 1905 and laid the groundwork for the paper on Brownian motion. Hoping it would bolster his chances, he also sent all of his published papers. Despite his impressive scientific achievements, of the 21 applicants, Einstein did not even make the short list of 3. It was at the behest of Alfred Kleiner, the professor of experimental physics at Zurich University, that Einstein tried for a third time to become a Privatdozent, an unpaid lecturer at the University of Bern. The first application was rejected because at the time he did not have a PhD, and in 1907 he failed a second time because he did not submit a Habilitationsschrift, a piece of unpublished research. Kleiner wanted Einstein to fill a soon-to-be-created extraordinary professorship in theoretical physics, and being a Privatdozent was a necessary stepping stone to such an appointment. So he produced a Habilitationsschrift as demanded, and was duly appointed a Privatdozent in the spring of 1908. Only 3 students attended his first lecture course on the theory of heat. All 3 were friends. They had to be, since Einstein had allocated Tuesdays and Saturdays. Since Einstein had been allocated Tuesdays and Saturdays between 7 and 8 in the morning. University students had the choice of whether or not to attend courses offered by a Privatdozent, and none were willing to get up that early. As a lecturer, then and later, Einstein was often underprepared and made frequent mistakes, and when he did, he simply turned to the students and asked, "Who can tell me where I went wrong, or where have I made a mistake?" If a student pointed out an error in his mathematics, Einstein would say, "I have often told you, my mathematics had never been up to much." The ability to teach was a vital consideration for the job earmarked for Einstein. To ensure that he was up to the task, Kleiner organized to attend one of his lectures. Annoyed at having to be investigated, he performed poorly. However, Kleiner gave him a second chance to impress, and he did. "I was lucky," Einstein wrote to his friend Jakob Laub. "Contrary to my habit, I lectured well on that occasion, and so it came to pass." It was May 1909, and Einstein could finally boast that he was an official member of the Guild of Whores, as he accepted the Zurich post. Before moving to Switzerland with Mileva and 5-year-old Hans Albert, Einstein traveled to Salzburg in September to give the keynote lecture, "The Cream of German Physics," at the conference of the Gesellschaft Deutsche Naturforscher und Ärzte. He went well prepared. It was a singular honor to be asked to deliver such a lecture. It was one usually reserved for distinguished elder statesmen of physics, not someone who had just turned 30 and was about to take up his first extraordinary professorship. So all eyes were on Einstein, but he seemed oblivious as he paced the podium and delivered what would turn out to be a celebrated lecture on the development of our views concerning the nature and constitution of radiation. He told the audience that the next stage in the development of theoretical physics will bring us a theory of light that may be conceived of as a sort of fusion of the wave and of the emission theory of light. It was not a hunch, but based on the result of an inspired thought experiment involving a mirror suspended inside a black body. He managed to derive an equation for the fluctuations of the energy and momentum of radiation that contained two very distinct parts. One corresponded to the wave theory of light, while the other had all the hallmarks of the radiation being composed of quanta. Both parts appeared to be indispensable, as did the two theories of light. It was the first prediction of what would later be called wave-particle duality, that light was both a particle and a wave. Planck, who was chairing, was the first to speak after Einstein sat down. He thanked him for his lecture and then told everyone he disagreed. He reiterated his firmly held belief that quanta were necessary only in the exchange between matter and radiation. To believe, as Einstein did, that light was actually made of quanta, Planck said, was not yet necessary. Only Johannes Stark stood up to support Einstein. Sadly, he, like Leonard, would later become a Nazi, and the two of them would attack Einstein and his work as Jewish physicists. Physics. And that's our last break. Around 3 pages left. Thank God. I think I'm giving myself a sore throat. I'll just quickly do one match. Never mind, the match can wait. Alright. To the finish line, y'all. Einstein left the patent office to devote more of his time to research. He was in for a rude awakening when he arrived in Zurich. By the time he needed to prepare for the 7 hours of lectures that he gave each week, the time he needed to prepare for the 7 hours of lectures that he gave each week left him complaining that his actual free time is less than barren. His students were struck by the shabby appearance of their new professor, but Einstein quickly gained their respect and affection by his informal style, as he encouraged them to interrupt if anything was unclear. Outside formal lectures, at least once a week, he took his students along to the Café Terrasse to chat and gossip until closing time. Before long, he got used to his workload and turned his attention to using the quantum to solving a long-standing problem. In 1819, two French scientists, Pierre Dulong and Alexis Petit, measured the specific heat capacity, the amount of energy needed to raise the temperature of a kilogram of a substance by 1 degree, for various metals, from copper to gold. For the next 50 years, no one who believed in atoms doubted their conclusion that the atoms of all simple bodies have exactly the same heat capacity. It therefore came as a great surprise when, in the 1870s, exceptions were discovered. Imagining that the atoms of a substance oscillated when heated, Einstein adapted Planck's approach as he tackled the specific heat anomalies. Atoms could not oscillate with just any frequency but were quantized, able to oscillate only with those frequencies that were multiples of a certain fundamental frequency. Einstein came up with a new theory of how solids absorb heat. Atoms are permitted to absorb energy only in discrete amounts, or quanta. However, as the temperature drops, the amount of energy the substance has decreases until there is not enough available to provide each atom with the correctly sized quantum of energy. This results in less energy being taken up by the solid, and leads to a decrease in specific heat. For 3 years, there was hardly a murmur of interest in what Einstein had done, despite the fact that he had shown how the quantization of energy, how at the atomic level energy comes wrapped up in bite-sized chunks, resolved the problem in a completely new area of physics. It was Walther Nernst, an eminent physicist from Berlin, who made others sit up and take note as they discovered that he had been to see Einstein in Zurich. Who made others sit up and take note as they discovered that he had been to see who made others sit down and take note as they discovered that he had been to see Einstein in Zurich. Soon it was clear why. Nernst had succeeded in accurately measuring the specific heats of solids at low temperatures and found the results to be in total agreement with Einstein's predictions based on his quantum solution. With each passing success, his reputation soared ever higher, and Einstein was offered an ordinary professorship at the German University of Prague. It was an opportunity he could not refuse, even if it meant leaving Switzerland after 15 years. Einstein, Mileva, and their sons Hans Albert and Eduard, who was not yet one, moved to Prague in April 1911. I no longer ask whether these quanta really exist, Einstein wrote to his friend Michel Bessot soon after taking his new post. Nor do I try to construct them any longer, for I now know that my brain cannot get through in this way. Instead, he told Bessot, he would limit himself to trying to understand the consequences of the quantum. There were others who also wanted to try. Less than a month later, on 9th June, Einstein received a letter and an invitation from an unlikely correspondent. Ernst Solvay, a Belgian industrialist who had made a substantial fortune by revolutionizing the manufacture of sodium carbonate, offered to pay 1,000 francs to cover his travel expenses if he agreed to attend a week-long scientific congress to be held in Brussels later that year from 29th October to 4th November. He would be one of a select groups of 12 physicists from across Europe brought together to discuss current questions concerning the molecular and kinetic theories. Planck, Rubens, Wien, and Nernst would be attending. It was a summit meeting on the quantum. Planck and Einstein were among the 8 asked to prepare reports on a particular topic. To be written in French, German, or English, they were to be sent out to the participants before the meeting and serve as the starting point for a discussion during the planned sections. Planck would discuss black-body radiation theory, while Einstein had been assigned his quantum theory of specific heat. Although Einstein was accorded the honor of giving the final talk, a discussion of his quantum theory of light was not on the agenda. I find the whole undertaking extremely attractive, Einstein wrote to Walther Nernst, and there is little doubt in my mind that you are its heart and soul. By 1910, Nernst believed that the time was ripe to get to grips with the quantum that he regarded as nothing more than a rule with most curious, indeed grotesque properties. He convinced Solvay to finance the conference, and the Belgians spared no expense booking the plush Hotel Metropole as the venue. In its luxurious surroundings, with all their needs catered for, Einstein and his colleagues spent 5 days talking about the quantum. Whatever slim hopes he harbored for progress at what he called the Witches' Sabbath, Einstein returned to Prague disappointed and complained of learning nothing that he did not know before. Nevertheless, he had enjoyed getting to know some of the other witches. Marie Curie, who he had found to be unpretentious, appreciated the clearness of his mind, the shrewdness with which he marshaled his facts, and the depth of his knowledge. During the Congress, it was announced that she had been awarded the Nobel Prize for Chemistry. She had become the first scientist to win 2, having already won the Physics Prize in 1903. It was a tremendous achievement that was overshadowed by the scandal that broke around her during the Congress. The French press had learned that she was having an affair with a married French physicist, Paul Langevin, a slender man with an elegant mustache, was a delegate at the conference, and the papers were full of stories that the pair had eloped. Einstein, who had seen no signs of a special relationship between the two, dismissed the reports as rubbish. Despite her sparkling intelligence, he thought Curie was not attractive enough to represent a danger to anyone. Even though at times he appeared to waver under the strain, Einstein had been the first to learn to live with the quantum, and in doing so revealed a hidden element of the true nature of light. Another young theorist also learned to live with the quantum after he used it to resurrect a flawed and neglected model of the atom. Oh my god. And that's it. I'm gonna stop the video right now. Yes. Alright, let me just look forward. There are 360 pages. We stopped at 66. We have around 300 more pages to go. And my voice is already disappearing as I consider what terrible, terrible things I'm going to put myself through. Woo! I love this.